Good afternoon, everyone. Today we're going to be continuing on with lesson 5.2, part 2. Yesterday we did 5.2, part 1. Section 5.2 in your textbook deals with multiplying and dividing radical expressions. So yesterday what we looked at is multiplying them. And the lesson to be learned from yesterday was that coefficients and coefficients can be multiplied together, and radicands can be multiplied together. We're going to have the same kind of rule today for dividing. So today and tomorrow we're going to be looking at dividing rational expressions. The important aspect to the lesson today, there's two parts to it. First of all, the radical expressions that we are dividing will primarily involve monomial radicals, radicals that have single terms. We're also going to be looking at something different though today, which is called rationalizing the denominator. So there's two kind of goals here. How do we divide radical expressions, and how do we rationalize a denominator of a radical expression? Well, how do we divide radicals? Very simply, we divide coefficients by coefficients and radicals by radicals. Very similar kind of idea to how we multiply radicals. You can only divide radicals that have the same index. What does that mean? Just like I said yesterday with multiplication, you cannot divide square roots by cube roots. You cannot divide fourth roots by square roots. The roots have to have the same index. Cube roots divided by cube roots works. Fifth roots divided by fifth roots works. Example number 1, divide. Express your answer in simplest form, always, and state restrictions on any variables in the original expressions. Well, the original expression here doesn't have any variables, so we don't have to worry about anything there. But we're asked to divide. Now, again, you are allowed to divide radicands with radicands. Don't forget, a radicand is the thing underneath the square root. So when we take a look at this expression, 960 is a radicand and 120 is a radicand. So when I say that we are allowed to divide radicands by radicands, what that means is this is going to be equal to the square root of whatever 960 divided by 120 is. And unless I'm mistaken, but I'll check it with my calculator, I believe that that's going to give us 8. 960 divided by 120. Yes, it gives us 8. So that means that our answer so far is root 8. But we've also learned that radicals are not simplified until any entire radicals are written in simplest form as mixed radicals. And in this case, root 8 can be written as root 4, root 2, and the square root of 4 is 2. So 2 root 2 is our answer. And I'm not saying that you should check every time, but we can certainly check this against our calculator by determining the value of the square root of 960 divided by the square root of 120, and then calculating the value of what we believe the answer to be, which is 2 root 2. Do that again, which is 2 root 2. And we get the same number. Let's take a look at 1b. Well, you know how I feel about negatives. I do not like that negative hanging out in front of the whole fraction, so I'm going to rewrite this to begin with as negative 7 root 256 divided by 14 root 32. And I'm going to use the rule that says I can divide coefficients by coefficients. This is a coefficient, this is a coefficient. And I can divide radicands by radicands underneath the radical sign. So I can write negative 7/14 multiplied by the square root of 256 over 32. Negative 7 over 14 reduces to negative 1/2. We need to simplify what 256 divided by 32 is. I'm pretty sure that that is going to be a whole number. 8 again. So we're left with another root 8, which we see quite often. So this becomes negative 1 over 2 root 8. Well, I mean, root 8 is root 4 root 2, which is 2 root 2. I think many of us will just know that root 8 is 2 root 2 without having to write this thing down every time. Anyway, now we have a coefficient of 2 on the top and the bottom, which can cancel. So our answer to this question is negative 1 root 2. And you certainly don't need to write the negative 1. This is the answer. At the end of each example, I'm just going to wait a short minute here just to make sure that everybody has copied things down. I can't see you, so I'm going to just assume that that was enough time. Let's take a look at C. We can rewrite C by taking the coefficient over the coefficient and multiplying by the radical of the radicand divided by the radicand. So 80 over 15, 15 doesn't divide into 80, but there is a common factor of 5. 5 times 16 is 80. 5 times 3 is 15. So we can reduce the 5. We can reduce by canceling the 5 with the 5 on the top and the bottom and being left with 16 over 3. 432 over 72. I'm not so sure that that divides without decimal, but we're going to find out. It does. 6. So we're left with a 6 under the radical. And then also r to the 5 divided by r cubed is r squared. I'm sure many of you don't have to write this step, but the square root of 6r squared is the square root of 6 times r. And since you have a pair of r's under a square root, we can write that as a single r outside. So we end up with 16r over 3, or 16/3 r root 6. Now we have to talk about rationalizing denominators. To simplify an expression that has a radical in the denominator, you need to rationalize the denominator. What does rationalize mean? Well, if the denominator has a radical in the denominator, if the expression has a radical in the denominator, then the denominator is not rational, because radicals are irrational. So to rationalize the denominator means to somehow make the denominator rational, and what that means is to remove the radical. In order to do so, as long as the radical in the denominator is a monomial, you multiply the numerator and the denominator by whatever the radical is in the denominator. Let me explain this. This is a little confusing, but if we take an example of 5 over 2 root 3, we have a root 3 in the denominator, which is not a good thing. We do not want radicals there. So what this rule is saying is you're going to multiply the top and the bottom of 5 over 2 root 3 by root 3. So I'm multiplying the top by root 3. I'm multiplying the bottom by root 3. Well, what do I get? I end up on the top with 5 root 3, 5 times root 3, which is 5 root 3. And on the bottom, I have 2 root 3 times root 3. But, and you will start to, I think, glean some information as to why this is going to be successful at this point. Because we have root 3 times root 3, which is root 9, which is 3, when we multiply the top and the bottom by that root 3, we end up getting rid of the root in the denominator. We end up having on the denominator 2 times root 3 times root 3, which is 2 times 3. And this 2 times this 3 gives us 6. So the answer is 5 root 3 over 6. Let's try a couple of these now in example form. Simplify each expression, 30 over root 20. Now, There are a couple of things that need to happen here. One is root 20 can be simplified. And that's going to need to happen somewhere along the way. The other problem is, the denominator contains radicals. In other words, the denominator is not rational. So we have to simplify root 20 and we have to rationalize the denominator. And I'm going to tell you right now, it doesn't matter the order in which you do them. I like to simplify radicals first. So if we do that, we have 30 over root 20. We can break into root 4, root 5, because 4 is a perfect square. So we end up with 30 over 2 root 5. And now we've created a coefficient on the top and the bottom which can be simplified. 30 over 2 is 15. So where does this take us? It takes us to 15 over root 5, and we've basically simplified the root 20. That's done. But now I have to rationalize the denominator, which says I'm going to multiply the top and the bottom by the radical that I'm trying to eliminate, which would be root 5. When I multiply across the top here, I get 15 root 5. When I multiply across the bottom, root 5 times root 5 is simply 5. The 15 and the 5 that I'm going to highlight, this coefficient and this coefficient can be simplified by division. 15 divided by 5 is 3, so I'm left with 3 root 5. Now, is there a different way we could have done this? Remember, so by the way, we've now taken care of that second item. Remember, I told you that you had to simplify the root 20 and you needed to rationalize the denominator. Well, maybe somebody wants to rationalize the denominator first. We have 30 over root 20, and we're going to multiply the top and the bottom of this expression by root 20 this time. That's going to give me 30 root 20 over 20, because root 20 times root 20 is 20. Again, I keep highlighting these coefficients because I think it's important that you're following what's going on here. Those two are numbers that are not inside of radicals, so this is what we call coefficients. 30 over 20 is 3 over 2, so now we have 30 root 20 over 2, and now I've rationalized the denominator. Now I can simplify root 20. We just did this, but I'll write it down again. Root 20 is root 4 root 5, which is 2 root 5. So I can write this as 3 times 2 root 5 over 2. I now have more coefficients that I can divide. A lot of ways that you can look at this. Some of you might prefer to say, well, 2 over 2 cancels. Some of you might decide to say that 3 times 2 is 6, and 6 over 2 is 3. In either case, we get 3 root 5. And if you want to check that against the previous work, we got 3 root 5. I know that many of you will want to know, well, which way should we go? And I don't think I can really answer that, because sometimes you might choose one path and it will be more work, and then the next time you choose a different path and it's more work. Let's take a look at example 2b. Again, what we're going to do is write this as root 60 over 75 with an x to the 8 on the top and an x to the 5 on the bottom. Now, I have a little observation for you here. If you are looking at this and you are looking at this, and you're really saying to yourself, who cares whether I write it as a radical divided by a radical or whether I write it as a single radical? In other words, if you're looking at that and saying, what's the difference? Then you've really understood so far what's going on. The bottom line is you can take that 60 over 75 and reduce it down. 60 over 75, 15 times 4 is 60, and 15 times 5 is 75. So that 60 over 75 reduces to 4/5. So I can write root 4 on the top, and on the bottom I will have a root 5. X to the 8 divided by x to the 5 is x cubed, so this is where we're at. Now what we can do is rewrite this as root 4 x cubed over root 5. So this is kind of interesting. We went from two radicals up here to a single radical. We did some work with the single radical, and then we went back to two radicals. Well, you didn't really need to put them as a single radical. You could have worked on this with the two radicals all the way through. Anyway, we can simplify the top of this. Root 4 is just 2, and we're left with 2 root x cubed over root 5 over root 5. There's lots of work to be done here yet. This is the interesting thing about radicals, is you'll do stuff and you'll think, oh, I'm almost there. But as soon as you do one more move, you create more work for yourself. And it's just the way it is. Before I rationalize the denominator, I'm going to write this as 2 root x times x times x over root 5. Of course, I have a pair of x's which can come out. So now I have 2x root x over root 5. And now I can rationalize the denominator by multiplying top and bottom by root 5. And I get on the top 2x. I have root x times root 5, which is root 5x. And on the bottom I have root 5 times root 5, which is 5. It occurs to me that all of these questions we should be looking at what are the allowable values of the variables. Let me go back and check. There were no variables in number 2a. I don't think there were any variables in question 1 at all. Oh, there was. So in terms of the original expression, and you want to be careful here as to how this is worded, it talks about restrictions in the original expression. And the original expression here in C has a square root of r to the 5. And what that means is that r must be greater than or equal to 0, because if r is negative, r to the 5 will be negative, and you are not allowed to take the square root of a negative. Getting back to where we were, we just completed 2b, and in the original expression, on the top we have a square root of x to the 8, and it doesn't matter in that expression if x is positive or negative, but on the bottom we have a square root of x to the 5, and if x is negative, a negative raised to an odd exponent will still be negative, and you cannot take the square root of a negative. So in the original expression, x must be greater than or equal to 0. C, negative 5/8, and then we have root of 5 over 7r. There really isn't much we can do with this, but I'm going to rewrite it as negative 5 over 8, and then I'm going to write this as root 5 over root 7r. And if you take a look at the coefficients there's nothing you can do with these two coefficients. There's nowhere you can go with 5 over 8. When you look at the radicands, 5 over 7r is a dead end as well. So there's really not much you can do here. Well, there's nothing you can do in terms of division, but we do not want a radical in the denominator, so I'm going to multiply top and bottom by 7r. On the top, what are we going to get? We have negative 5, and then we have root 5 times root 7r, so we can multiply 5 by 7r and get 35r. And on the bottom, we have an 8. And then root 7r multiplied by root 7r is simply 7r. So we are going to get on the top negative 5 root of 35r over on the bottom 56r. Now let's do a check of some things. Can we divide this coefficient by this coefficient? Well, we can, but it doesn't simplify, so we're not going to. If we do the division, we'll get decimals, and we don't want that. Is root 35 something that can be simplified? Meaning, is there a perfect square that divides into root 35? And the answer is no. Are there any radicals in the denominator? No, which is a good thing. So we've done all that we can do, which means that this is the answer to the question. All right, final example. Simplify each expression. So we have a root 40 in this expression and we have a root 20. The thing that makes example 3a different than anything we've looked at is the top of the expression is a binomial. But let's clean up root 40 and root 20 first. I like to do this off on the side someplace. Root 20 is root 4 root 5, which is 2 root 5. Root 40 is 4 root 10, root 4 root 10, which is 2 root 10. So these two radicals, root 40 and root 20, are radicals that you should be able to simplify fairly quickly. So let's rewrite this with those simplified radicals. We have 14 minus 2 root 10 over 2 root 5. Now this is very similar to quadratic results from the quadratic formula. You cannot do this. That's not allowed. You cannot do that. That's not allowed. But you can simplify by factoring a 2 out of the top, and I'll show you the shortcut in a second. But if I factor a 2 out of the top, I'm left with 7 minus root 10 over 2 root 5. And now you have a factor of 2 in the numerator and denominator, which can be canceled. And I've spent a fair amount of time going over that again and again and again in this course. The shortcut is to essentially take these three numbers that I'm highlighting and divide them all by the same number, 2, leaving us with, I'm just going to rewrite it, 7 minus root 10 over root 5. But that root 5, this is a problem because it's in the denominator. So how are we going to handle that? We're going to multiply the top and the bottom of this expression by the square root of 5. Leaving us on the top with 7 times root 5, which is 7 root 5, minus root 10 times root 5, which is minus root 50, over 5, because root 5 times root 5 is 5. No, we're not done. Because root 50 can be simplified. That root 50 can be written as root 25 root 2, which is 5 root 2. So our actual final answer will be 7 root 5 minus 5 root 2 all over 5. I'll give everybody a minute here just to make sure that you've got everything written down before we look at what I think might be the last example in this lesson. Three root 6 plus 12 all over root 18. Again, I'm a big fan of simplifying those radicals before rationalizing. 18 factors into 9 and 2, where 9 is a perfect square, so root 18 is root 9 root 2, which is 3 root 2. So I'm going to replace the root 18 with 3 root 2, 3 root 6 plus 12 over 3 root 2. I notice that these three numbers, I'm going to start relying a little bit more on a shortcut here. These three numbers, which are all coefficients, are all divisible by 3, so I can do that. I'm going to divide the 3 root 6 by 3 to get root 6. I'm going to divide the 12 by 3 to get 4. I'm going to divide the 3 root 2 by 3 to get root 2. Again, I don't want a radical in the denominator, so I have to multiply top and bottom by root 2. Giving me on the top, don't forget, you have to multiply that root 2 and distribute it into the root 6 and the 4. So I end up with root 12 plus 4 root 2 all over 2. Are we done? Okay, so you have a checklist that you need to go through. Did you remove all of the radicals from the denominator? Yes. Can you divide any radicals by radicals? Well, since there are no radicals in the denominator, no, you can't. Can you divide any coefficients by coefficients? Well, only if you can reduce this coefficient, and this coefficient by the same factor. But the first coefficient is 1. So there's no work to be done there. What about, are all radicals simplified? Well, no, because root 12, I'm really hoping that almost everybody knows root 12 is 2 root 3, but to go through it again, 12 is 4 times 3. So root 12 is root 4 times root 3, which is 2 root 3. So if I put 2 root 3 here, then I have plus 4 root 2 over 2. Be a little lazy here. These coefficients now all have a factor of 2 in them. So at this point in time, we can reduce all of those highlighted terms down by a factor of 2, leaving us with root 3 plus 2 root 2. I suppose we could check that against the original question. Let me just run that through my calculator. It's been a while since we did this. Root 3 plus 2 root 2 is this number. If I go to the original question and I take 3 root 6 plus 12, and I divide that by root 18, I get the same number. So that's it. I've mentioned this many times before in this course, but it's getting to be especially true. You need to do a lot of practice to be successful. So my recommended practice problems for this section are on page 8 of the unit handout. It's questions 1 through 5. I hope that made sense to you. I'm going to be away tomorrow as well, so tomorrow you'll have another video lesson. And one of your goals, I guess, or assignments or requirements moving forward for Monday when I return is to make a list of all of the questions that you need help with. So Monday may very well end up being a catch-up day where we spend most of the class going over practice and questions you have. Anyway, have a great rest of the day and get to work. We'll talk to you later.